Our electric grid, the thing that powers literally everything in our lives, is going through this massive, once-in-a-century transformation. We're all in on clean energy, right? Plugging in huge amounts of solar and wind. But here's the thing. This shift is creating a huge, kind of hidden problem for the grid's stability. So what happens when the very things that have kept our lights on reliably for 100 years just start to vanish?
And look, this isn't some far-off theoretical question. This is the real deal. It's what grid operators all over the world are trying to figure out right now. For decades, our entire grid was built around this one type of technology that gave it this natural, rock-solid stability. And as we unplug those old power plants, we're literally pulling out the foundation. So what exactly is this magic ingredient we're losing?
For 100 years, the whole show has been run by these guys, synchronous generators. Just picture these enormous, super heavy spinning machines. They're hooked up to turbines that are pushed by steam or gas or water. And the key thing is their sheer rotating mass is all physically locked in, perfectly synchronized with the grid's rhythm, kind of like a giant, steady metronome for the entire country's power system.
And all that spinning weight gives the grid something absolutely critical. It's called inertia. Think about it like this. It's a lot harder to stop a massive freight train than it is to stop a little bicycle, right? Well, that physical inertia from those generators acts like a giant shock absorber for the grid. It helps keep the flow of real energy, what we call active power, in perfect balance. So when something goes wrong, like a power line gets knocked down, that inertia just naturally fights the change, slowing everything down and giving the system precious seconds to sort itself out.
So here's the deal. This slide really shows you just how fast this change is happening. In the past, it was all about those big spinning machines. That meant we had a grid with tons of inertia and what engineers call high system strength, which is basically its ability to keep the voltage steady. But today, we're swapping them out at an incredible pace for solar and wind, which connect through power electronics called inverters. And the future? Well, it's a grid powered almost entirely by these new resources.
And here's the bottom line. As we lose that physical spinning mass, we lose inertia. Plain and simple. The grid gets, well, weaker. Or maybe a better word is more elastic. It just doesn't have that built-in shock absorber anymore. And that makes our entire power system way more sensitive, more fragile. Small problems can blow up into big ones a lot faster, putting our reliable electricity supply at risk.
Okay, so to really get why this is happening, we've got to look at the technology that connects pretty much all of our solar and wind farms to the grid today. And the key word to remember here is follower.
This piece of tech is called a Grid Following Inverter, or GFL for short. You can think of it as a super smart device that acts like a current source. Its whole job is basically to listen very carefully to the grid's voltage signal. It uses this clever system, a phase-locked loop, to lock on and then inject its power in perfect time. But its entire design, its whole existence is based on one massive assumption, that there's a strong, stable grid out there to follow in the first place.
All right, I love this analogy because it makes it so clear. The old grid with all those big synchronous generators was like a sturdy lead bicycle in a group ride. It had weight, it had momentum, it set a clear, confident pace and direction. It basically created this super stable path for everyone else to draft behind.
Now, today's grid-following inverters, they're like those little tag-along bikes you attach to the back. They're awesome at adding power. They can pedal like crazy and push a ton of energy into the system. But here's the catch. They can't steer. At all. They just have to follow wherever the lead bike goes. And you can see where this is going, right? If you keep adding more and more tag-alongs while your lead bike gets smaller and weaker, the whole train starts to get really, really wobbly.
So if the problem is too many followers and not enough leaders, well, the solution seems pretty obvious, doesn't it? We have to create new leaders. And that is exactly what this next generation of technology is built to do.
Say hello to the Grid Forming Inverter, or GFM. This is a total game changer. It uses a completely different playbook. Instead of just listening and following, it leads. It actively forms the grid. It creates its own super stable internal voltage and frequency. It acts like a voltage source, just like those old generators did. And get this, it can be programmed to provide synthetic inertia, which is an electronic way of creating that same shock absorber effect we've been losing.
And here it is, the solution in action. In the grid of the future, these grid-forming inverters become our new sturdy lead bicycles. They don't just add power, they create the stable path themselves. They put out that rock-solid signal that lets all those thousands of other grid-following resources, all our tag-along bikes, connect to the grid safely and do their thing without making the whole system unstable.
Okay, so let's just put these two side by side for a second, because it really all comes down to this one fundamental difference in how they see the world and how they interact with the grid.
I mean, the difference is really night and day. Grid-following inverters are passive, they're dependents. They listen to the grid and just control the current they push out. But grid-forming inverters, they're active, they're leaders. They create their own voltage and lead the grid, directly controlling both voltage and frequency. One's a follower, one's a leader. It's that simple.
This chart just makes the difference so obvious. Doesn't need a strong grid? The follower does, for sure. But the leader, the grid-forming one? Nope. It can actually work on its own, even creating its own little island of power. Can it provide that all-important inertia? The follower can't, but the leader is designed to create it electronically. But here's the real kicker, the absolute game changer, black start. Can it restart a grid after a massive blackout? The grid-forming inverter can. That one capability is huge for making our grid tougher.
Okay, so if this technology is so great, what's the catch? How do we actually start building it into the grid we're going to need for the future? So the most important thing to get is that this isn't an either-or situation. We don't have to rip everything out and replace it. The future grid is going to be a hybrid. We don't need every single solar panel or wind turbine to be a leader. We just need to strategically place these grid-forming inverters, usually hooked up to big batteries, to act as the new stability anchors for the whole system. They make the grid strong enough for everyone else to connect to.
But, and it's a big but, there's a major roadblock. It's this classic chicken and egg problem. So step 1, grid operators are seeing these stability issues and they know they need grid-forming tech. But then step 2, they can't really force developers to install something that isn't widely available or standardized yet. Which leads to step 3, manufacturers don't want to build factories to mass produce the stuff without clear rules and guaranteed demand. And that takes us to step 4, developers just build what's required and cheap, which is the old follower tech. And that brings us right back to the original problem. It's a frustrating loop.
But here's the good news. That frustrating loop is finally starting to break. All around the world, people are getting serious about this. In the UK, they're creating new markets to actually pay for grid stability. In the US, the government is funding major research to create the standards everyone needs. And in Australia, they're already putting these grid-forming batteries in the weakest parts of their grid. The ball is finally officially rolling.
And I think this quote just nails it. Grid-forming technology is basically the key that unlocks the door. It lets us add way more solar and wind to the grid safely. It's a powerful new tool that helps the people running the grid keep the lights on for all of us, even as those old spinning machines retire for good.
So, the bottom line is this. The technology to solve one of the biggest challenges of the clean energy transition isn't just an idea. It's not science fiction. It's here. It works. It's the key to making a 100% renewable grid a reality. So the question we have to ask ourselves isn't if we can do this anymore. It's how fast. How quickly can we line up the rules, the markets, and the standards to get these new leaders deployed and build the strong, resilient, and completely clean grid we're all waiting for?